Alright friends, today we're going to review some of the ideas on voltage, current, and resistance that we've used before. Some ideas about electrical energy and power that we've talked about before. Some ideas about parallel and series circuits that we've done before. And try to introduce some rules that will help us to analyze more complex circuits. So this is a type of circuit that we would not have been comfortable analyzing previously, and with the help of the rules of Mr. Gustav Kirchoff, we're going to be able to make some headway on them. So just as a couple of points to hit at the beginning of this. So we've talked about resistance and current before, but something I just want to drive home one more time is that current is not the whole story. Okay? So if you have a wire and you have a certain number of charges that are passing through a surface per unit time. Okay? Remember, current is measured in amps, which is in terms of coulombs per second. That does tell you something, but it doesn't tell you about what all of those individual charges are doing. And it also doesn't tell you about what's happening at different points within the wire in the circuit. So this idea of current, it's bundling together a lot of information. It's integrating over what we call the current density. So this J is that current density, which would have a unit of coulombs per second per meter squared. So amps per meter squared is our current density. And then you take it and multiply that current flux that's going through the surface and do the dot product with some area and integrate over that, and that gives you the current. Likewise, the resistance is not really just a single thing. It's a number that we can measure, but it's sort of a higher level concept that integrates a bunch of different things. In a simple model that we developed in the last video, for instance, it depends on how long your resistor is. It depends on how big the cross-sectional surface area of the resistor is. And most importantly, it depends on the resistivity of the material. So it combines together material properties and geometric factors. So just to sort of drive this idea home, let's consider what happens if we have a current of 2 amps running through a circular conducting wire with a radius of 0.5 centimeters. Okay, so there's our 0.5 centimeters, which is 0.005 meters, and it's some sort of a wire, a circular wire. Part A asks, how many electrons are passing through any cross-section of the wire per minute? So this is actually just a unit conversion problem. If I've got a current of 2 amps, well, an amp is just another way of saying a coulomb per second. Coulomb is units of charge, seconds are units of time. If we want to find out how many electrons are passing through any cross-section per minute, well, we have to convert coulombs to elementary charges. So this would be 1.602 times 10 to the minus 19th coulombs is 1 electron charge. And then for seconds to minutes, we could go ahead and say that 60 seconds is 1 minute. Okay, so this would then, we could cancel out coulombs, cancel out seconds, and this would give us something in terms of electron charges per minute. Okay, so that would be your 7.5 times 10 to the 20th electrons per minute. And then in part B of this type of problem, it says, assuming the current is uniformly distributed through the wire, what is the charge density J in the wire? And I notice this is a typo. This should be current density J in the wire. Current density if you have this whole surface having the same current density, this would just reduce to I equals J times A, or your J would be equal to your I over A, or it would be I over pi R squared in this problem. So this would be 2 amps divided by pi times 0.005 meters squared. Okay, so that's where I'm getting this number, 2.5 times 10 to the 4th amps per meter squared. Now, a good thing to compare, just since we're doing both types of components in our lessons, what is happening with energy in capacitors versus what is happening with energy in resistors? Well, you'll remember that we have this expression for the energy stored in a capacitor, 1/2 CV squared. Now, what is happening? Why is that energy being stored? Well, the reason that we have energy stored is that we have plus charges on one of those plates, we have minus charges on the other one of those plates, and between the plates we have an electric field. So you can equivalently think of the energy being stored because we have the charges that are that can exert forces on each other. Equivalently, you can also think of it as being from the charge from the electric field itself holding that energy between the plates. So a capacitor doesn't make energy leave your circuit, it just holds energy. So if you hook up your capacitor to a battery like this, so this is my picture of a hooking up a battery, there's my plus minus side of your battery, is connected to a capacitor. The capacitor is not it's not dissipating energy from your circuit, it's just holding energy that used to be in the battery. On the other hand, if you take a battery and hook it up to a resistor, so there is my squiggle, 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 that's my resistor. There's my plus minus. You have a current that goes through the battery, and as the current goes through the battery, you constantly lose energy. The particles that were accelerated by the electric field in the battery, they're going over and over and over, and then they lose energy as they go through the resistor, and once they've lost that energy, they now, that energy is radiated as heat. So that P equals IV, power is in terms of watts, which is joules per second. And then over here, our I times V is going to give us something that's also in terms of joules per second. I is in terms of coulombs per second, amps, and then V is in terms of joules per coulomb. So this is amps times volts gives me watts. So now here is a quick capacitance energy homework question that I gave you this week. Now, on the one hand, this is sort of an easy question because you're just going to use your formula, U equals CV squared. And they say, what capacitance, so they want you to find this, is required to store an energy of 10 kilowatt hours at a potential difference of 1,000 volts. Okay, so on the one hand, pretty easy. All you're finding is the capacitance, you've got everything else. But the tricky part of this problem is that they've given you the energy in a weird unit. 10 times kilowatts, so 10 times 10 to the thirds, watts times hours. So this is an energy because it's energy per time times an amount of time, but it's weird because hours, this is in joules per second, and this is in hours. So let's quick see how we're going to convert that into joules. So this is watts. Let me just write that as joules per second. Joules over seconds. Okay, so 10 times 10 to the 3 joules per second times hours. And then now I can go ahead and say that 1 hour is going to be 60 minutes. And 1 minute is going to be 60 seconds. And then so surprisingly here, you end up, your hours cancel out, your minutes cancel out, and your seconds cancel out. So it gives you something that's in terms of joules. Okay, so there's your energy in joules. Volts, you're going to have to take 1,000 volts squared, and then you're going to find your capacitance, and in the end of the day, that's going to be in farads. Now here's another problem that's sort of interesting because the math is easy, but the concept is a little it's a little hard to figure out what to do. So let's read about this. It's having us deal with some antique technology. The CD player has a storing power saving, special power saving technology. The manufacturer claims that with only 2 standard AA batteries, together they have a voltage of 3 volts. Okay, so V equals 3 volts. And they store 20 kilojoules of energy. Okay, so there I'm going to have my U, essentially, the amount of stored potential energy is going to be 20 times 10 to the 3rd joules. And the player can be played for about 25 hours. So there's my T. And my good units on T are seconds. So 25 hours, I can always go ahead and transform that into seconds. So 1 hour is going to be 60 minutes times 60 seconds, so 60 squared seconds. Then it asks the question, what is the approximate resistance in the CD player's electrical circuitry? Well, the thing that we need to notice in this problem is that we have power as the only thing that has anything to do with energy. So P equals IV. Power is energy used per unit time. So in this problem, our P would be that U over T, the amount of energy that I have divided by the amount of time it takes to spend that energy. So my U over T is going to equal IV, but I times V, I want to find the resistance. That's what it's been asked. So I can go ahead now and rewrite this equation in terms of the resistance. How am I going to do that? Well, V equals IR, that's my Ohm's law. So I'm going to go ahead and write my I in terms of V over R, and then I'm going to stick that into my P. So my P equals V squared over R, but my P is my U over T. So let's just write that. U over T equals V squared over R, V squared divided by R. And then if you want to find your R, you can go ahead and solve for it. So my R is going to be V squared times T over U. Okay, so you just need to stick in 3 volts times this T in seconds divided by this U in joules, and that should give you something around 40.5 ohms. Okay, so no real tricky math in that one, but it is kind of hard to weave your way through all of the concepts. Now, something I would just want to point out to you is that the equation for our resistors in series, last time we talked a little bit about the equivalent resistance as sort of an analogy to the equivalent capacitance. And this equivalent resistance has a similar form for the series and the parallel for the resistors versus capacitors. Okay, so even though all of the physics is pretty similar for series and capacitor circuits, the problem is that Q is the charge type of thing, but I is the charge type of thing in the resistor equation. So in the capacitance equation, Q is the thing that has units of Coulomb. In the Ohm's law, I is the thing that has units of charge. It has amps, so it's coulombs over seconds. So if we wrote this in a similar way, it would be I equals 1 over R times V. So unfortunately, the equations are flipped for our resistors and our capacitors, because instead of having something in the numerator in this type of equation, we have something that's in the denominator. The bigger the resistance we get, the smaller the current. And remember, the bigger the capacitance we would get, the bigger the stored current. So that's a little tricky, and we kind of have to keep ourselves honest and be on our toes. Okay, so we do have to be on our toes, but it's not bad. All right. So let's look at this. Let's look at a couple easy examples. So this is about as easy an example as we're going to get of resistors in series. Okay. So this is not in parallel. This is in series. It says if each resistor in this picture has a resistance of 2 ohms, so this is 2 ohms, this is 2 ohms, what current is produced when the battery supplies a potential difference of 12 volts? Well, together these are acting like a resistor with an equivalent resistance of 4 ohms. If this is 12 volts, V equals IR, and if we want to find our current, I equals V over R equivalent. So our current would just be 12 volts over 4 ohms. Current is 3 amps. All right, nice. Not so hard. Let's take a look at a problem using resistors in parallel. So in this problem, it says we've got a bunch of light bulbs connected in parallel to a 120 volt source as shown in the figure. Each bulb dissipates an average power of 60 watts. So P equals 60 watts. The circuit has a fuse F that burns out when the current in the circuit exceeds 9 amps. So I max equals 9 amps. Determine the largest number of bulbs which can be used in this circuit without burning out the fuse. Okay, so 60 watts. We have 120 volts. Now we know that P equals I times V. Now each of these light bulbs in series, and in fact if you think about it, each one of your outlets in a regular house is wired this way. You have 120 volts in each one of your outlets. So your house is wired in parallel. The power is going to equal I times V. So we know this 120 volts. We'll learn in a couple videos that it's actually a little more complicated than this because it's AC voltage, but let's live with the illusion for now. So we have 60 watts equals I times 120 volts. So the I here would be 0.5 amps. If our maximum current is 9 amps, that means if we took 9 amps divided by 0.5 amps, we could get 18. So the total number of bulbs that we could get if we were just trying to go up to 9 amps but not over would have to be a maximum of 18 light bulbs. Okay? So each one of these is going to have a current of 0.5 amps. Okay, so this is so far so good. Now let's try to think it through and see if we can do problems where it's not so clear whether our circuit is a series circuit or or a parallel circuit. So this circuit that I'm showing you right here in this picture seems to have a combination of the two. And so this would be a nice tester quiz question where it says, what is the approximate equivalent resistance of the 5 resistors shown in the circuit? Now I'm going to redraw this a little bit because the way that it's drawn right now, a lot of students look at this and say, this looks to me like those two are in parallel. But remember, I can redraw this however I like, just so long as I don't break any wires. So I'm going to do this. I'm going to draw it like this. There's my 5 ohms. And then I have 2 ohms. And then right here and here are going to be 5 ohms and 2 ohms. 5 ohms, 2 ohms. Okay, and then finally at the bottom I'm going to put 7 ohms. Now it might look like this is very different, but all I've done is I've stretched out this bottom wire a little bit. I've stretched out this one. Now I hope that you can see these two are in fact in series. So I can treat that as an equivalent resistor of 7 ohms. But once you do that, you can see that these two are in parallel, and so I can treat this as being a 2 ohm and a 7 ohm resistor in parallel. So 1 over 2 plus 1 over 7 equals 7 over 14 plus 2 over 14 equals 9 over 14. And then I need to take the flip of that to get that my equivalent for those two in parallel is going to be 14 over 9 ohms. Okay, and I can take my calculator and go ahead and find what is 14 over 9. 14 divided by 9 is about 1.6. Okay, and at this point I have a 5 ohm, and I'm now treating this whole thing as about a 1.6 ohm resistor, and then followed by a 7 ohm. So 5 plus 7 is around 12, and then 12 plus 1.6 would give me 13.6, and so the one of these that's closest would be 14 ohms. Alright, so there's kind of a lot going on there, and we had to think a lot. Now, if you are going to do this a lot, and you were going to try to teach a computer how to unsnarl circuits, you might want a little bit more of a systematic way of doing that. And so that's what Kirchoff's laws gives us. Kirchoff's laws let these snarly tangled be untangled. And they do it with physics. And so essentially Kirchoff's laws use 2 principles. The first principle is that the sum of all the changes in potential around a loop must be 0. Now what this means is essentially energy conservation. If my charges in my current are going to gain energy here, the amount of total energy that all of them lose must be the same as the amount they gain right there. So it's kind of an aggregate statement. So just to see what this means, if I had these as my basic components, I'm going to have some voltage across the first one, some voltage across my second resistor, some voltage across my third resistor, and they have some weird looking E as the voltage of my battery. No, that's bad. The weird looking E is for the EMF, but I don't like this notation, so I'm not even going to discuss it. So if you go through the battery in the direction of the current, we count that as a positive voltage. If you go through a resistor in the direction of current, then we count that as a negative voltage. So here we're going to have minus V1. We're going through this resistor in the direction of the current, minus V2. And then we're going to go through the resistor in the direction of the current, minus V3. And then we say that equals 0. So the way that you would use this then to solve a problem is to use then Ohm's law. So V equals IR, so this would be minus I times R1. Same current goes through R2, so it would be minus I times R2. Minus I times R3. And then you could use this to go ahead and solve for your I's, solve for that current. Now, you might even notice we already sort of secretly used this principle when we did our equivalent resistance for resistors in series. Now, the junction rule is a sort of restatement of charge conservation, and it just says that if you have charges going in, it has to equal the charges going out. So when you set up a circuit and you first off guess what direction you would expect the currents to be going in, and then you draw in the junctions, and then you have all of the incoming circuit, all of the incoming currents equals the sum of all of the outgoing currents. Okay, so for like this particular junction, our rule would be I naught equals I1 plus I2. Now, let's look at a really sort of a snarly circuit. This one is one that we couldn't have done with what we've talked about previously. And the reason we couldn't have done it is because it has 2 batteries in it. All right? So let's see how we're going to use Kirchoff's laws to get this done. So the first thing that we do is we guess what direction we think the currents are going to be going. Now, in this one, we've drawn in a current I1. That's going to be the same I1 that goes through this battery, and that's going to be I1. Okay, so this, we guessed the current in this wire. It doesn't branch off, so we have to stay self-consistent. Next, we guessed that the direction of the current going through this resistor is going to be to the left. So that's fine. Then I need to be consistent, and so the same current goes through my battery. So there's my I3. Same current goes through this 2 ohm resistor at the top. So there's my I3 as well. And then I have an I2 going up. So it doesn't need to be right. If you get it wrong and you guess the wrong direction, then your I will just turn out to be negative, and then you would have to realize that the direction of your current would be opposite what you guessed. So what are we going to do first? Well, first let's go ahead and do the easy one. Let's look at our junction right there. All of the ingoing currents have to equal the sum of the outgoing currents. So I2 that's our ingoing currents, equals I1 plus I3. Now I could have used the bottom junction as well, then I would have gotten I1 plus I3 equals I2. In this case, that doesn't give me any independent information. Okay, so that's done. I've used my junction. Now, there are a couple different loops that you could use. You could use this loop, that loop, or the loop all around the outside. Now, the two that are going to be easiest to use are going to be the loop on my left and then the loop on the right. So let's go ahead and do it. So this is going with the direction of the current through the battery. So I'm going to have my 6 volts. And then this is going with the current through a resistor. So that's going to be minus the voltage. So I1 times 8 ohms. This is going through the resistor in the direction of the current. So it's going to be minus I2 times 5 ohms. And then we're going to finish our loop up right here, minus I1 times 4 ohms equals 0. So we went all around the loop, and the sum of all of those voltage hikes and drops equals 0. And then we do the same thing right here. So let's start at this battery. So 6 volts minus I3 times 6 ohms minus I2 times 5 ohms minus I3 times 2 ohms equals 0. Now, depending on how comfortable you are with math, you may or may not see that I'm done with this problem. I'm done with all the physics. I'm done in the sense that I have 3 linearly independent equations and 3 variables. I1, I2, I3. So since I have 3 equations and 3 unknowns, I can now go ahead and solve. So I'm not going to do that in this video. I'm thinking about whether I want to do it in the next video or not, because to me it seems like once you have the idea, it's not actually that much more illuminating to go ahead and solve it. But I want you to at least understand this is how you would teach a computer to solve more complicated circuit problems. So what do I want you to take away from this video? We talked about current and resistance and how they're related to current density and resistivity. We talked about how circuits in houses are wired in parallel and how that has some important consequences. And then we talked a little bit about how Kirchoff's laws let us untangle complicated circuits by applying energy conservation, that's the loop rule, and charge conservation, that's the junction rule. Okay, so thanks for watching, and good luck on your homework.